Dear students, today's class is about production of X-rays. Now, we all know that X-ray was discovered, or you can say invented, somewhat accidentally. Now, how it was discovered, or how can you produce X-ray for 12 purpose? We are not going to the history of that. So we all know that in a gas discharge tube, you can say, when at extremely low pressure, about 0.1 millimeter mercury pressure, we all know that normal atmospheric pressure is 760 millimeter mercury pressure, but about 0.01 millimeter mercury pressure, that is extremely evacuated chamber. When a high potential difference is applied, electrons comes in form of streams of electrons, you can say, comes out of the cathode and strikes the wall of the anode. This is how cathode ray is formed. But what happens if the voltage difference is increased further? Further means here, just see the arrangement there. It is a very updated discharge tube where we have written that about 50 kV to 100 kV, 50 kV to 100 kV potential difference. That means at about 50,000 volt to 1 lakh volt potential difference is applied, and extremely evacuated chamber, 0.01 millimeter mercury pressure. Electrons come out of the cathode with tremendous velocity and strikes the wall of the anode. Now what will happen to the kinetic energy of the electrons? This has to be shifted to another form of energy. That is the arrangement made here, that anode becomes so heated that water jacket has to be applied there. That is water jacket, it flows down to cool somewhat the anode. And high tension is applied there, low tension is applied at cathode. So electrons, when strike the wall of the anode with such a tremendous velocity, that results the generation of X-ray through those windows. W1, W2 are the windows. X-ray are coming out. So what is the case there? At a highly evacuated chamber, 0.01 millimeter mercury pressure, and a great potential difference, about 50 kV to 100 kV is applied, electrons coming out of the cathode with tremendous speed, tremendous kinetic energy, and striking the wall of the anode, resulting in generation of electromagnetic waves with very short wavelength and high penetrating power. These are called X-rays. Now, if the potential difference is more, approaching 1 lakh volt or more than that, then you will get hard X-ray, and if the potential difference is lesser, then you get soft X-ray. Hard X-ray means more penetrating power. Soft X-ray means less penetrating power. Hard X-ray means shorter wavelength, higher frequency, and soft X-rays means greater wavelength, lesser frequency, and less penetrating power, of course. So this is how X-rays are produced. Now, uses of X-ray, we all are aware of that in medicinal purpose, mainly to determine the fractures of bone, etc., X-rays are used. X-ray have a great use in future physics when you go in higher classes, suppose in graduation or masters, even after that, X-ray crystallography, solid state physics, to determine the nature of a metal, how does it behave when X-ray passes through the surface of the metal. So it will be helpful. And then again, the Bragg's law. Bragg's law depends on diffraction. We know that Bragg's law is when X-ray passes through the metal surface. Suppose these are two rays we have taken two rays there. First light ray gets reflected at the upper surface, second light ray enters the second surface and gets reflected from there. So if we just see the figure there carefully, we will see that second ray actually traveled a bit farther. That means it has traveled a more path, QP plus PR. QP plus PR is the path difference between the rays, first ray and second ray. and we have a relation between the path difference and wavelength. So path difference equals to wavelength multiplied by n. We have the phase, same phase in other part, that is in wave optics. We will know about that. So here only the application of Bragg's law, that is path difference is multiplied by an integer to the wavelength, that is the light rays are in same phase. Then we have 2d sin theta equal to n lambda. From what we can get the separating distance between separating surfaces of a metal, d, that is. So it is useful for that. And now one more thing, that high energy is what E equals to, from Bohr's theory we know that E equals to h nu, and so E equals to hc by lambda. H nu equal to c by lambda, so we have E equals to hc by lambda. That means the higher the energy, the shorter will be the wavelength, that is the relation between energy and the wavelength there. From that we can also calculate the wavelength of the X-rays which are emitted after the electrons are striking the anode surface. That's it for it, but for the class, for the production of X-rays. But another thing, that is the graph of continuous X-rays and characteristic X-ray. Now why these X-rays are evolved? The electrons are hitting the anode surface with tremendous velocity, generation of X-rays taking place. Fine. In case of elements with less atomic number, metals with less atomic number, you can get the X-rays at a lower voltage, like 10,000 volt or beyond that, from 10,000 volt, 20,000 volt, etc. But more higher the atomic number of the element, X-ray production takes place at higher voltage, about 20,000 volt, 25,000 volt. Suppose in case of tungsten, X-ray starts to come out about 20,000 volt, like that. And if you just increase the voltage difference, harder will be that is with more penetrating power. Now if you increase the temperature, if you increase the voltage 25 kV, 40 kV, 45 kV, 50 kV, 70 kV, you will see another phenomenon, graphical analysis. Beyond that continuous curve, you will see some peaks, not drawn here, but just have some peaks there. That is called characteristic X-ray. Just you will continue to get continuous X-ray, and somewhere you will get some peaks like that, sharp peaks. Why those peaks again? If electrons strike there at the surface of anode and energy is coming out in form of X-ray, continuous spectrum or continuous X-rays were fine. But what about the characteristic X-ray? The peaks, explanation of those peaks. Those peaks can be explained as the electrons hitting the anode surface, entering the inner part, inner orbits, and just you can say pushing out, emerging out those electrons from the inner orbits. Now you know in case of higher atomic numbers, the attraction between the nucleus and the inner electrons is terrific. So you need to have a lot of energy to just push out the electron from their orbit. So this energy is involved there, and when those orbits becomes empty, electrons from higher orbit comes to those lower orbit, and in this process they are releasing huge energy. That release of energy in X-ray spectrometer can be seen as peak, those peak. So K alpha, K beta, K gamma, K delta lines, from which orbit they are jumping to the lower orbits, depending on that. So that is the explanation of continuous spectrum as well as characteristics, or continuous X-rays as well as characteristic X-rays. From that evidence, Henry Moseley, who was just you can say doing the work on characteristic X-ray, has come to a phenomenal conclusion that atomic number is directly dependent with the frequency or wavelength or frequency of the X-rays, and from that he told that the properties, the periodic properties, or you can say the physical and chemical properties of the elements, are the periodic function of the increasing atomic number. there is a relation that root nu is the frequency, root nu is directly proportional with Z. Z and nu, atomic number and frequency, are directly proportional to each other. So there is a relation between them, and from that he came to conclusion that periodic properties or the physical or chemical properties of periodic function of their increasing atomic number, which is known as modern periodic law. So from X-ray we also explained the modern periodic law. That's it for the class. Thank you.